let's begin.
Okay, so what sections shall we read, and what time shall we reconvene?
I think so. For this, if we look at the text, it's not much, but yeah, it's we will take some uh, understanding. It will take some understanding to run through the code. Uh, yeah, we should reconvene in 40 minutes. I think so. That will be more than sufficient for this. If,
We stopped at training architecture last time, the section on training
Mhm.
architecture. So should we just read the rest of the chapter then, or
Yep,
what?
we should read the rest of that. But I would like to dedicate this next time. I will try to dedicate this uh, session to overview of some popular RL algorithms, and I will I'll take a look at these uh, one, two, three, four, five, six. These six algorithms later. So we can do that too. And maybe last time I shared if you're done through the uh, text and the books uh, notebook which is given there, we can also take a look at the TensorFlow's agents tutorials that are there from the environment, the drivers, the DQN, the policies, the replay buffers tutorials too, because that will also
Okay,
yeah.
but for today, what should we do for today?
I think so. We should read through those sections and run through the code.
Okay, okay.
Yeah.
And when will we reconvene at 11 o'clock? I mean,
Mm,
11 o'clock Pacific? That's 45 minutes.
yeah. Yeah.
Okay,
Yeah.
yeah, okay.
So, I forgot to share my screen. Let's begin. Hello. I think we are ready to start. If you guys need some extra time, and please feel free to.
It's not yet 7 o'clock. Maybe we can start at. Maybe we can start after 3 minutes.
Oh, let's start. So, mm, can you guys see my iCharm and the Chrome window, the book? Yep. Let's start to begin. Uh, the, yeah, training architecture. So last time we 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 looked at the environmental wrappers for the Atari preprocessing, the environment specifics, the TF agents, uh, and now we will take a look at how the DQN is formed inside TF agents, and the architecture that we will be using here. It's a pretty much flexible and scalable architecture. So let's begin. This is two, uh, the figure 18.13 represents the TF agents training architecture. These are two parts. That's the collection part and the training part. And these two parts can be run in parallel. On the left, uh, if we go through the uh, various, mm, the first is the environments. The first one is the environments. Mm, The yeah, here we can have multiple environments that we require here. The second one is these environments are the breakout games that we can run in parallel, and the driver. Then this driver comes into play. This explores the environment using the collection policy that's there here. Uh, and it allows us to choose the actions. Uh, this is the actions that we get from the collection policy, which is again passed here. And based on that, we get the time steps, and we then this driver uh, passes on the trajectories to the observer here, which saves those uh, trajectories in the replay buffer. Uh, and then this is the one step that is being performed. The second is the training part. This is the data collection part. The second is the training on which the agent pulls the batches of trajectories. So this is the agent just pulling the data set, these batches, and uh, from the replay buffer and train some networks. Uh, this is being pulled from here. It's training this network here, and uh, mm, uh, this network is being then used by the collection policy. This is the network that we are training, and these predictions are being passed on to the collection policy here. So there's a two-way interconnect between this collection policy and the networks. and uh, the single way between how the data flows from the replay buffer to the data sets, the training that's being taking place here. So this is a kind of a online learning in which the training and the data collection, it's happening uh, together, uh, explores it and collects the trajectories where the rail part learns and updates the policies. So this is the scalable architecture here, because we can have multiple drivers here too. If we scroll down, and then yeah, they have explored this multiple environments, multiple copies of an environment in parallel. Then the advantage of the CPU cores keeping the GPU busy for the training part. Yeah. This is also applicable in the ES algorithms. The ES is uh, a bit different from tensor, this RL, uh, which stands for evolutionary strategies. So it's a kind of algorithms that uses the ideas that we have in our biological evolution to how do I say it, to solve problems. So uh, these kind of architectures are used there too. Um, this is with respect to the taking advantage of all the powers on your CPU cores, those multiple uh, and environments that can be run, and those data collection and the training is performed at the same time. Then they have defined the trajectories. That's the sequence of consecutive transactions from time step n to the time step n plus t, which where t is the number of the current time step, and those trajectories that are collected by the driver are passed to the observer, and then it performs uh, uh, those how do I say those sampling distributions from the replay buffer, and that depends upon epsilon greedy or any other type of prioritized um, uh, sampling strategies that we had seen earlier. Then observer, why do we need it? And since the driver can save it into the replay buffer directly, this will result into the architecture that will be a kind of which will have less flexibility here. Why do you want to use because if we want to use the trajectories for computing a metric with respect to uh, uh, suppose uh, kind of comparing it with an optimal policy or a metric that uses some number of uh, average rollouts or something else to uh, have some sort of how do I say it uh, observations of how our policies on the replay buffer is kind of interacting, and what's the optimal policy with respect to some sort of metrics that are being used. So that makes sense from a research perspective in which you are trying to fine tune it, those matrices for giving optimization to those uh, small control problems. So that's why we need that. And uh, you can use an observer. They've also given a point as to use an observer to save the trajectories to a replay buffer or to save them in a TF records file. Yep. TF records is an example of, as we have seen in chapter 13, which compresses it, those in the TensorFlow format and the protobuf that makes it in a particular protocol that uh, uh, allows it to easily distribute it, distribute the training data across the network. If we are having multiple uh, nodes or multiple uh, in a data cluster, so that training will help in from that fashion. Uh, so that's a distribution strategy that helps, and I've used that at this of course makes a big difference if you are trying to use raw images versus saving them to a TF record file and then using protobuf to distribute and train those simple. So you will see a huge difference in the performance of the uh, network, and the saturation of the GPUs will increase here. And then the author gives a tip to customize it as you please, because all of these classes are inheritable, and we can use a custom environment. And if we are using a custom environment, then we can use a environment package, and which overrides and methods such as action spec, observation spec, underscore reset, and underscore step. We will see this in the creating a custom TF agents environment section of the notebook. So, any questions here? This is pretty cool if you see it from a practitioner's point of view. And there are multiple. Uh, there is mainly everything that is required here to, other than some small uh, optimization steps that I missed. This TF agents provides everything that's required to scalable for us from a scalable research point of view. So,
Hey, Mike,
yeah.
question. You know that on the right-hand side of that figure,
Mhm.
figure 13, there is a small blue box inside of agent that then expands out to collect policy. I'm not sure I understand what that means. Do you know? Do you have an insight into what that means?
So the agent, when is trying to update the policy, since it's training of on that particular data set. So this is a kind of an online uh, learning kind of a scenario, reinforcement learning. So at we can have a certain time period or certain steps after which that policy is being updated with respect to those trajectories that we saw earlier. So uh, maybe if we, yeah, we,
Okay, I guess another question is, it seems like in my head I have this view of reinforcement learning as, you know, the agent is trying some strategy and then collecting some data, and then kind of rewinding and trying another strategy and collecting another, seeing what happens again. And I don't see where the rewind step is. So do I have it wrong, or?
Rewinding with respect to the training of the algorithm. Uh, yeah, that's subpart. That's with respect to if you're, I think so. You're referring from a rewinding perspective.
I'm just thinking, maybe I don't understand the whole picture, but it seems like the agent is trying a strategy, but then he backs up and tries another strategy, and then he backs up and tries another strategy. So he's not continually moving forward. He's trying a bunch of strategies in parallel, and then these strategies are getting, the outcomes of the strategies are getting collected into a replay buffer or something, and then some optimal decision is made by looking at all of the results of the exploration agent. Do I have that wrong?
I don't think so. Yep, that's in overview from a overview perspective. That's correct. But you need to look at the agent from uh, that backup policy, that the backup strategy that you're trying to describe. That's uh, how will an agent back up if it it will try to sample from some 3 or 4 trajectories that suppose if I try to let's draw a agent, a robot here. Suppose it has one way to reach this goal here. Let's consider the MDP here, simple, and a set of rewards. Uh, we have a goal state here. This we can define as G1. This we can define as G2. So uh, uh, each circle here represents 10 points, for example. So here is 10, here we have 10, 10, and 10.
Is that
So
10 steps or?
some there is this is some rewards. So yeah, those time steps, and with respect to those actions, uh, we uh, yeah, we will have to make a grid if uh, we have to define this. But yeah, consider this a boxed environment.
Mhm.
And suppose this is the n number of time steps that this is in a box, and it reaches G1 goal state with a reward of 20. And this is another n time steps, which the agent reaches goal state G2 with a reward of 30. So this is 20 here, this is 30. So uh, after those trajectories have been collected, so it will try to sample the best possible policy to reach a particular goal state here. So this agent, suppose its name is B, uh, this agent B will store this will have the collection of these policies with respect to the G1 and the G2 states, and uh, it will store them, and then for the next and if we have a epsilon greedy being applied here, then it will select this G2 goal state here, and then this agent will be here from for the next time step, and we are taking those time steps as n here. So from here, those next 4 grids will be taken, and then that agent can sample this with respect to how the policy has to be taken. So this is the updates that I was referring to dynamically with
So,
predicting
so,
and yeah.
so what is the significance of the number 4 in this example?
This is the number of, if we look at it from how do I say it? Tabular perspective, then this agent is trying to explore this four neighboring uh, goals, these four neighboring uh, uh, environments, not
Mhm,
environments, four neighboring, you can say rooms, or
mhm, mhm.
this
And
is
each
the
one is
max that,
opened
yeah,
by each one of the rooms is opened by an initial action.
yeah, and
Okay.
initial action and those value pairs. So
And this is the evolution of what happens if you take that action toward and you proceed towards the goal. Is that?
yeah.
Um, and so in the cart pull example that we have,
Hmm.
is there just one goal, and that is to keep the pole from tipping? Or are there two goals, or are there more than two goals?
Yeah, in the end goal is one. It's just one that we need to make sure that those agents do not that pole stays upright for as long as possible.
Mhm.
So that's the main goal, and on the basis of that goal, we are trying to model everything.
Mhm.
Uh, so yeah. So this is the angular velocity, the position, and the velocity here. So we are
Mhm.
trying to model everything just on the basis of uh, uh, this.
Okay, so we just want to keep the angle and the angular velocity within the right range,
Mhm.
so that the pole will be vertical. What about the breakout environment? What are the goals in that environment?
So the goals in the breakout environment will be
Mhm.
to take all those bricks
Mhm.
and score the maximum points here. So every brick that we hit uh, uh, is associated with a particular point system, and it shouldn't. It of course constrained by the number of rules, and every time the ball touches this guy here, pad, then the speed increases. So the rules of the game have, since we are not giving the rules here, and uh, it has to learn to train according
Yeah.
to, yeah. So that's the strategy that we have.
So it gets a reward for knocking a brick out, and it also, does it die if it misses the paddle? If the ball misses the paddle, does the agent
Yes,
die?
yes. The paddle, if the ball misses the paddle, the agents die, and yeah.
Thank you.
Hmm. So this is the collection policies. If we date the collection policies, yeah. So as defined, those policies are being updated with respect to reaching those particular uh, states with the value iterations, or some other uh, internal policy, some other internal updations that have been applied here. So uh, the policy here, of course, refers to the directories and the state action howsoever your MDP has been formulated. So those policies are updated like that. Uh, Next, we take a look at creating a deep queue network here. Uh, then TF underscore agents network package. We take a look at this package here. So just add. I was exploring this before uh, we jumped on to the call. So this is the package, the networks package. If you can see, and it has all these Python files and classes. And we import queue network from here, and then what we do is we apply some pre-processing layers with respect to this guy. Let's create a queue network. Yeah.
So on this code, it's pretty clear what it's doing to create the queue network. It's a succession of steps that specifies what the network has to look like. But the only question that I have about this is why is the last layer have 4 outputs? What's the significance? Again, I'm going back to this number 4. Why is the number 4? Why is the number not 1?
We're talking about this board here. Is
Yeah,
the stride of four?
Yeah, it says that the dense output layer has 4 units with 1 Q value to output, 1 per Q value to output. So is it by default evaluating 4 different actions? I'm looking right under the code, under that code that begins with pre-processing layer.
Okay, starts with pre-processing symbol lambda
Yeah,
layer.
that's the one. Yeah, that's the code right above that. Yeah, and he says that the dense output layer has 4 units. Yeah, it's a little bit farther. Let's see. Right after the 512, there's a dense layer with 512, so it's just a few lines down from where your arrow is.
Yeah.
Yeah, a dense output layer with 4 units, 1 per Q value to output. So are we by default evaluating 4 different actions? Is that what this is doing?
Yeah, there are 4 different 1 unit per action. So yeah, if we see, yeah, it had actions, vision.
Because you didn't tell it about that 4. That seems to be a default. It seems to add that last layer by default, the last layer with 4 fully connected layer with 4 output parameters is added by default, it appears, because it's not specified anywhere in that code.
The 4 here, I think so, refers to the left, right, the fire, and one more action.
Oh, this is specific to the breakout game, or?
Yeah, this is specific to the breakout grade.
Oh, I see.
I was just looking at where those steps have been.
Yeah.
Yeah, because I can see this. Yeah, action meaning. Yep. In environment.gem.get action. Yeah, I think so. They haven't mentioned it here. Mhm. This is the environment step. This is the environment that we have loaded here.
Uh, I see something with 4. The env gem get action meanings. There's no op, fire, right, and left.
Mhm.
Is that the 4 things, or maybe not?
Yep. No, for right and left.
No
Yeah,
fire, right,
because
and left. Yeah.
yeah, and since this is being output, this dense uh, layer is out. So yeah, if we you can see this here on the right. This is a no fire right and
Mm-hmm.
left,
Mm-hmm.
and under the hood that we get from the fully connected layers, it will be this. Where was the code? Fully connected, fully connected. Followed by a dense output layer with 4 units, one per Q value to the outputs. That is one per action. Yeah. So
Okay, 1 per action. Okay, so that's like true or false for each. So like each output is like a one hot encoded version of that.
yep, it seems like it. Yeah.
Uh-huh, uh-huh.
Because under the hood, if we take a look at it from under the hood, that Q network class, that's the Q network class that we are uh, uh, initializing, and these are the parameters here. So these are the parameters, the observation specs, the uh, action specs, the pre-processing, the con layer parameters, the FC layer parameters, and this is the encoder network here. And then we have the Q value layer here.
Yeah, that makes sense that it's 1 per action. There are 4 possible actions.
Hmm.
So, and so it's going to output the output should be a one hot vector with zeros everywhere you don't, zeros for all the actions you don't want to take and 1 action that you do want to take.
Hmm.
So there has to be a 1 somewhere. So like if the, if the ball is just waiting to hit the paddle, then for example, then you would take a no op step. And
Hmm.
then if once the ball is going in the right direction, I'm not sure when you would fire in this case or what fire means.
Fire, I think so, means at the first the instance, uh, when the environment is loaded and when the pad has the ball that is in the breakout. I
Uh-huh.
don't think so. Yeah.
So it's just,
I
there's just one time when that happens.
yeah.
The initial
Yeah.
trajectory is set, and then it can go. Let's see. Okay, so then I'm not sure what no op means. It's moving. It has to move either right or left.
Or the
Um,
no option. You just have to stay still there.
no op is just staying still.
Yeah.
Why would you want to stay still? Oh, because
Because
you want to
if
wait for the paddle to move to the right place.
or if the ball is coming back to the same location, so you do not want to move in the next time step. You need some time to determine, or the velocity of the ball
Mhm.
is right there. Yeah. So it's
So is a
since
right left? Does right left mean an acceleration or like can the ball change directions instantly or does it have to glide? Um, does it
uh,
have to move with constant velocity?
oh, when the ball hits the paddle,
Mhm.
it increases its or whatever the rules are because
Yeah, it increases its
yeah.
velocity, they say. Yeah.
It
So
increases its velocity. So after a certain number of steps, the velocity will be too high, and
yeah. And the ball you can't make the ball change directions, right? If it's moving to the left, it has to move in a constant velocity along that direction, right? You don't get to change its direction instantaneously, do you?
mm, yeah, if it's moving to the left, then yeah, unless it hits the wall and it
Mhm.
changes or
Then
a
it
particular
changes, yeah.
brick, yeah.
Okay. Okay. So now I understand no up. No up is weight, is basically weight,
Mhm.
and it's not going to stay put. It's going to keep moving in the direction it was already moving, right?
Yeah.
And then, so I understand no up, and but what's left and right?
Now, left and right is simply moving the paddle to the left and right.
Oh, moving the paddle. Okay, got it, got
Yeah.
it. Okay, now I understand. Okay,
So those
great.
four actions are being applied to the paddle.
Okay.
So fire, no up, left and right. So that's the
Oh,
output we
okay.
get from the dense layers.
Okay.
That's this tf.char as the layers.dense. This is the
Okay,
activation, the
got
bias.
it.
Yeah.
Got it. Thank you. That makes that clear.
This is the initialization, and in the call, we are just passing on those state and the training values. Yeah. So those Q value and the network states that we get. The observation and the step type and the network state. This is the internal of the Q network. Mm, That I think so. Yeah, these two paragraphs discuss on. So, uh, lastly, if we see the architecture of the encodings, so here are the pre-processing layers. We can have multiple inputs to it. They have given an example of more than one camera inputs, or some two, or some other inputs from, like if you are trying to train a robot, then we might have LiDAR and radar inputs too. So we
Mhm.
can have those pre-processing steps that inputs that can be scaled, that goes from 0 to n here. So this pre-processing layers can go to n, and then this is the pre-processing combiner, which combines if the pre-processing is greater than 2. If yeah, it's pretty much intuitive here. If we take a look at the preprocessor combiner in the encoding networks, just I was exploring this, and yeah, this is the pre-processing combiner. If it is none, if it is not none, then we copy those layers. And in the case that it's greater than 2, if it is 1, then we process it, and then those combining of those pre-processing layers are all also mentioned here. So that's the comment. If only one observation is passed and the pre-processing combiner is unspecified, use the pre-processed version of this observation. If not, we have to combine it. Yeah. So that is with respect to combining multiple sensors data. Suppose if we have a, robot and we have a control problem, uh, then And if a robot has a pair of cameras and radar, then those three inputs can be combined in this function. We can pass this pre-processing combiner to here. This is the pre-processing combiner parameter. Yep, this which is being used with the CNNs and then we have those convolution layers and those fully connected layers, which gives us the output. So we can mix and match this and tweak it to combine those outputs here, and then we use the con layer and the FC layer. So that's the architecture that we looked at. This is this convolution and dense is, of course, we looked at. We had a we we looked at it in the CNN's part of this book, and we can also apply a dropout after each dense layer to increase our generalization and our accuracy. That will also work. We will, of course, have to experiment with those parameters, but yeah, that will work fine. Then the author gives a note as to the Q network class and why is it flexible enough to always build your own network if you need extra flexibility. Yep, we can extend this network class and use it like custom keras layer. Yeah, we can add some functionalities that is required by the agents, such as create a shallow copies of the network. Uh, uh, the DQN agent uses this to create a copy of an online model that we looked at it earlier, that copy of that online model, and then we had after each 58 iterations, we use that to uh, have those streams be guided by that. So this we looked at in the last lecture. So this is the node that we can extend it. And then coming out, moving forward to creating a DQN agent here. Let's create a DQN agent here, converting Python environment to a TF environment. I think so. We have covered this. Yeah, we had covered this last time. We creating a DQN agent now. Yep. So here, what we have tried to do is firstly count the number of training steps. We have used the train step variable here. Then the update period, and that's the 4. Why 4? We have why is the training steps used every 4 collection steps, because we have to determine the velocity of the ball. So we need at least 4 frames there. We discussed this last time too. And this is the optimizer. And these are the hyperparameters from the DQN 2015 Nature paper. The learning rate 2.5, E minus 4, the decay 0.95, momentum 0, epsilon 1E, 1, 2, 3, 4, 5, 1E minus 5, the centered is true. Is the epsilon function, which schedules a polynomial decay. That's also from the DQN 2015 paper. So here we start from the initial epsilon of 1 and we go to the final epsilon of 0.01. And this is the number of decay steps per update period. So this is As you can see, the graph will be like polynomial decay. Then we construct a DQN agent here, and these are the parameters that are required. Here, if we look at the DQN agent, here we had the time steps spec, TF in with respect to the TF in environment, the action spec, uh, here the four actions that we had specified, the QNet that we just defined, the optimizer that we had, yeah, the target update period that is 2000, which corresponds to 3200 frames. Yeah, sorry, 32,000 frames, sorry. Uh, then that's the TD error loss function. Here we use the Huber loss. Here the loss function must return an error per instance and not the mean error. And that's why we have used reduction is equals to none here. So if we haven't used this, it would have given a mean error. The gamma is the discount factor, the train steps, and the epsilon function with respect to the train steps here, the epsilon greedy approach that we are using here, that we defined the polynomial decay. So after initializing with all those parameters, our agent is ready. Yeah, and we call the agent dot initialize, and the agent can now get some action here. Okay, now let's go on to creating a replay buffer. Uh, then this replay buffer, uh, well, in TF action, we are using this TF uniform replay buffer package and the TF uniform replay buffer class. The data spec will have those agent.collection.collect data spec. This, yeah, is from this agent, and the batch size and the max length. That is the 1 million. I hope. 1, 2, 3, 4, 5, 6. Yeah. 6 zeros, 1 million. Yeah. Uh, so these are the attributes from the 2015 DQN paper. Those same hyper parameters, and we add those replay buffer observer here. Yeah. Now we take a look at the batch size is the batched in environment. Where it's kind of a offline. We call it nowadays offline batched reinforcement learning. When in which uh, we take a batch of actions at each step and return a batch of observations, and those, as we alluded to earlier, those driver would have to save those batch of trajectories, and using the TensorFlow's replay buffer, it will handle the computational graph, and yeah, it will try to parallelize that environment. Of course, they have also given a kind of a parallel PY environment package. Uh, yeah, it makes uh, sense to run those multiple environments in parallel. They can be used across the action and the observation specs. Yeah, they can become combined, and then yeah, it makes a lot of sense to have a distributed running a environment and then use this. Uh, then we have the max length. This is the replay buffer, the maximum size, and of course this will require that much RAM. Mm, So this batch size is with respect to a parallel. I was just discussing about the parallel PY in environment. That is with respect to uh, a number of parallel environments in a particular machine. But if you want to have a distributed that is spread across multiple machines, then it's a bit different. Uh, and then we take a look at the this tip, which has the py hashed replay buffer, in which the hashing of those four frames, since those four frames will be repeated, and those three frames, if we take a look at the three of the four frames in the second observations, which are kind of redundant here. So uh, those hashed replay buffers can be used to deduplicate that data in the stored trajectories along the last axis of the observations. So this saves a lot of memory. Mm, Then we write those trajectories in the replay buffer. Yeah, replay buffer observer is equals replay buffer dot add batch. Uh, this takes a trajectory argument. Um, if we want to create our own observer, we can write with any function with a trajectory argument. Then we need a class with a simple dunder method of call with a self and trajectory method. Um, Here is a simple observer that will increment this. They have given an example of an observer here that will give a increment a counter every time it's called here. This is a simple show progress class that is defined here. Then we have added some training metrics. It's simple with respect to the number of episodes, the environment steps, the average return metric, and the average episode length metric that we have. And that's the result with respect to the shape of this. This is the number of episodes. That's the D type, and yeah. The author also gives a note as to use the discounting for the training and to implement a policy. And we also discussed it in one of the last lectures here, why discounting is important and how good it was by summing the undiscounted rewards. What can we do? Yeah, so the average return metric here computes the sum of the undiscounted rewards and then tracks of the streaming mean of these sums over all the episodes it encounters. So it's a good metric to have. I haven't used this in my average return metric for my graphs, but yeah, this looks good. And then we have those results, and we can log all those metrics by the logging APIs of Python. Yeah, these the get logger at the info level. We are saving it. Yeah, that's pretty simple actually. Now let's go on to the collect driver method, the collect driver uh, part of it. Okay, we will go through creating a collect driver, and we will try to end it because we might shoot overtime. So here the collect driver is an object that explores the environment using a policy experiences, collects the experiences, broadcasts to the other observers. And in at a high level, these are the three steps. We discussed it. We alluded to this earlier too. The driver passes the current time step to the collect policy, which uses this time steps to choose an action and returns an action step object containing that action. And the driver then passes the action to the environment, which returns the next time steps. And finally, the driver creates a trajectory to represent this transition and broadcast it along to all the observers. I gave an example of the four rooms, a simple uh, tabular example, which we use this here. And these are some policies, such as the RNN policies, are stateful. Uh, what stateful here means is they choose an action based on both the given time step and their own internal state. So that's how the stateful policies are defined. And on their these stateful policies with respect to those MDPs are formulated with these three four parameters in mind. So this is a high level intuition as to of how everything works, the data flow and the steps that we use to uh, 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 get our how do I say it, those sequence of actions that we require. So that's the control flow that goes through our program, and they in the end what they're doing is they're training a stateful policy here, and it simply samples a trajectory and set the policy state to the state in which the time of this a sampled time step. So uh, this is the main thing of the main reason DITRA, what happens while training a stateful policy here. Uh, so, and then they give an example of a batch time step to the policy. That's the time step object containing the batch of observations, batch of step types, a batch of rewards, and a batch of discounts, and where all the four batches are of same size here. So let's look at the code here. The driver, the dynamic step driver and the dynamic episode driver. Yeah, this is it. So we have passed in the TF environment, the collection policy, the observers have the replay buffer observer plus the train metrics, and the number of steps, that is the update period. And this will be 4. So uh, mm, this is with respect to the batch trajectory that we are constructing. Uh, then after collecting the initial experiences just before the training, this is the initial collect policy, which is specified by this random TF policy class. Uh, Here we have the time step specs and the action specs. which are paths. And then we have the dynamic step driver, which has those environments, initial collect policy, and observers, and the number of steps, which will correspond to these many frames. And then we init the driver and run this. So this is the collection of this is the bootstrapping process, if you can see it from that perspective too. How those random TF policies are initialized. It's the same as how we initialize our convolutions with the Xavier or some other sort of initializations just before we train our network. So let's stop here since we are already over time. Any questions up until now? Okay, cool. I think if everything is clear, I think I did a great job, and I should pat myself on the back then.
Yes, definitely.
Yeah.
Yeah.
Cool.
Thank you so much. Yeah. So we're, I guess next time we'll finish. I noticed that, and I think somebody else noticed that the Colab notebook doesn't run. I couldn't get it to run, and I think somebody else tried it also. I did get the notebook to run on my own machine, but I have a GPU with Windows, and I was able to get it to run. But if you don't have a GPU on your machine, then it, you know, if you get it running on Colab, let me know. But I didn't get it running on Colab.
So I've made some progress, Joseph.
Oh yeah.
I thought I had finished it, but once I got past where I was erroring out before, I have a few more at the end, and it just looks like some particular parameters are not set correct. Not parameters, but variables are not set correctly. But once I finish it, I will post it. I don't have access to a GPU, so I have to make it work.
Yeah,
So,
yeah. Well, definitely interested in hearing how you got over the error that you mentioned before, because I had that same error.
gotcha. Well, the two things that I have at this point is that first instruction. You know what? I have some notes here, and I'll just post those in the
Great,
chat.
that'd be great. Great,
I'll just post what I have so far as an issue, and then I'll post the rest later.
Thanks, because that would be really terrific if we could get it running on Colab, and then everyone can see, everyone can be able to see how beautiful this thing works.
Okay, will do.
All right. Thanks, everybody. And thank you, Mayank. It's really great to have somebody that knows the subject to lead us through. So we'll finish it on Wednesday, right?
Yep.
All right.
All right. Thank you, Mayank.
Thanks, everyone.
Thank you,
Thanks,
Mayank.
everyone.